to a lecture series on linear algebra. In the previous lecture, we have been discussing about the linear dependence and independence of vectors. In this lecture also, we are going to continue with the same. Right. So in R3 of R, we were talking the linear independence and dependence of few vectors in the previous lecture, I hope. Now let us continue with the same. Right. Let me take my in the previous video we have seen till S4, right? So let me take my S5 to be 1 1 1, okay, 1 2 1 and 2 2 2. This is my collection, right? So here I am just going to verify whether this forms a linear dependent set or independent set, right? Let me write x times of 1 1 1 plus y times of 1 2 1 plus z times of 2 2 2, and this is to be equated with 0 0 0. So what am I going to get? I am going to get x plus y plus 2z, x plus 2y plus 2z, x plus y plus 2z, which is to be equated to 0 0 0. And when I try to write that in a matrix form, I will get 1 1 2 1 2 2 1 1 2. Right? Here you can see the two rows are equal. If two rows are equal or identical, then we will get what? The determinant of matrix to be 0. Even if either of the two rows or two columns are identical, we will get the determinant to be 0. Here exactly we have, if you see the rows, these two rows are equal. If you see these two columns are identical. That is why you are getting your determinant to be 0, which means what? Your set is a linearly dependent set. Okay, the given set is a linearly independent set. Let me take my S6 to be my S5, right? My S5 union, I have one vector, right? What kind of set it is going to be? Let me write it. Okay, so I have x of these things the same. Let me directly write that. Okay, x plus 2y plus 2z, x plus y plus 2z. Along with this, I have w times of 110, that is w 0, which is to be equated to 0 0 0. So finally what I am going to get is x plus y plus 2z plus w, x plus 2y plus 2z plus w, x plus 2y plus 2z plus 0, which is to be equated to 0 0 0. When you write down the matrix of this thing, right, so you get 1 1 0 here. What is the maximum rank of this matrix? The maximum rank of this matrix can be 3, right? But you have what? 4 unknowns, right? In that case, you will not have it to be linearly independent. This is also linearly dependent, right? Therefore, with this, let me remark one thing that you can see in the see downwards. That is, if you have some linearly dependent set, any superset of that set is also linearly dependent, right? Let me repeat it. If you have any linearly dependent set, any superset of the linearly dependent set is also linearly dependent. Okay, let us get into another example. That is, let me choose, I have gone till S6, right? Let me choose my S7 to be 1 1 1 1 0 0 1 1 0, right? So we have proved, this was my something, right? We have proved it to be linearly independent. Now let me choose my S8 to be S7 minus 1 0 0, which means what? I have only 1 1 1 and 1 1 0. Let me see what is going to happen here, right? It is alpha times of 1 1 1 plus beta times of 1 1 0, right? It is to be equated with 0 0 0. So here what am I going to get? I will get alpha plus beta, and again alpha plus beta and beta, which is 0 0 0. This clearly tells me my beta is 0, therefore my alpha has to be 0. Even if I choose like another element from here, the same I am going to get, right? So here you can see that any subset here, it is a S8 is a subset of S7, okay? S7 is also linearly independent. Here we have a general result, a remark that we can make from this problem is that any subset of a linearly independent set is also linearly independent, right? Let me repeat, any subset of a linearly independent set is also linearly independent, right? Now let us see a few more problems on R3 of R. Okay, here let me start the counting fresh. It is 1 1 1 with 2 3 4 and 3 5 6. So this is one set. I have another set 1 1 1 and 2 3 4 3 5 7 and 11 12 13. S3 is 1 1 1 and 2 7 9, and S4, let me have this to be 1 1 1 and 1 1 0, and okay, this we have checked, I suppose, so let me take it to be 1 0 1. So let us have these four things and let us examine for the linear dependence or independence, right? Here one more thing that I forgot to remark, that is, if we have only two sets in the vector, that is in the set, only two vectors in this set, a kind of this one, right? If one vector is a multiple of another, then that is linearly dependent. If not, they are linearly independent. What do I mean by multiple of another? Let me take in a general sense, okay, v1 v2 v3, this is what we have, right? Suppose this is to be equated to 0, okay, it may be any number of vectors, right? So it need not be till 3, it may go on till n, any number, right? So we have something of this sort. Suppose if you take this to that side, what will you have? Alpha times of this thing is minus beta times of this thing. You must have something of this sort, right? So when you have your u1 u2 this thing, when you take this to the side, all these are taken from where? These are taken from a field. If it is non-zero, you have the inverse exist, right? So you may write beta upon alpha of v1 v2 till vn, right? When you have your alpha is 0, that then clearly tells you that your beta has to be 0, okay? We need not go till this, so this is going to be something like this, okay? Even if you have something in common of all these vectors, you can take that too outside. So from this, what you have, your vector is some scalar multiple of another vector. If this is so, this is linearly dependent, because I have told you just before, I have told you that you assume your alpha to be a non-zero value. If your alpha is a non-zero value, then beta is also a non-zero value, because alpha non-zero implies beta non-zero here. So you have this is a scalar multiple of this. In this case you will get it to be linearly independent. The point that I am trying to convey here is two vectors, okay? Two vectors are said to be linearly dependent if one is a multiple of another. Okay, if one is not a multiple of another, then the vectors are linearly independent. Okay, now you can see that this is not a linear multiple of this, sorry, scalar multiple of this, or this is not a scalar multiple of this. So this is linearly independent, right? Now let us check other three things. Okay, as of now, for time being, let me not write the complete things and try to get the matrix. Let me write down the matrix directly. So it is going to be the first one is going to be something like this. I will have to check the rank of this matrix, right? And next, if I try to write down the matrix, it is going to be next week, yeah, right. So 5, 12, that is 1, 4, 7, 13. Okay, and the last matrix is going to be 1, 1, 1, 1, 1, 0, 1, 0, 1. Sorry, I think I have made a mistake here. Yeah, this is not the matrix. The matrix is 1, 1, 1, 2, 3, 4, 3, 5, 7, 11, 12, 13. Okay, now you just find the rank of these three matrices. The rank is going to be 3 in this case, and here also you will have the rank, the rank is the rank is going to be 3 in this case. The rank is not going to be 3 in this case. Okay, so we have 4 unknowns. Here the maximum rank is 3. So the rank is not going to be 4, therefore it is not linearly independent. This is linearly independent, and here you will have 1, 1, 1. When we do the elementary transformation, 0, 0, 1, and 0, 1, 0. Right. So here also you are getting the rank to be 3. Therefore, it is also linearly independent. Right. So if you have any queries in this lecture, you can post it in the comment section. That will be clarified within 24 hours of time. Thank you for watching.